All right, so we're back after a little technical difficulties. We are now back to lecture 11. I'm going to give my little speech again that this is the point in the course in which math becomes a much bigger issue. We'll be doing heavier math for the rest of the year. That being said, you wouldn't be in this class if your math was not good enough to be here. So if you're struggling, we can support you. If you like math like I do, you're going to be happier as we move forward. So we're going to talk about Chapter 11, which is the last chapter on Term 2, Test 1. And chemical reactions can absorb or release energy depending on the relative strength of the bonds being broken and the bonds being formed. So, thermochemistry. What is thermochemistry? Study of transfer of energy in the context of chemical reactions. So, what would be an example of thermochemistry that we care about, like in the real world? Explosive chemistry, explosions. Yes, that is definitely thermochemistry. There's one that I would argue most people utilize on a daily basis. Combustion of gasoline, yes. We also heat our houses through chemical reactions. We get electricity, all these things. So, thermochemistry. So we have our 3 laws of thermodynamics. The first is the energy of the universe is constant. So we'll talk about that on the next slide. Second, the entropy of the universe is always increasing. Whoops. So we'll talk about this later. We're going to spend a lot of time with entropy later in the year. I like to think of entropy as just disorder or kind of chaos. And the entropy of a perfect crystal at 0 Kelvin is 0. And this is like a bookkeeping thing. So the first law of thermodynamics, the energy of the universe is constant. Can somebody rephrase this for me? Perfect. And we talked about this as one of our pillars, one of our fundamentals in the lectures that you watched over the summer. We talked about the conservation laws of mass and energy being one of our 4 pillars of chemistry. So energy can't be created or destroyed. We can quantify energy change in a chemical reaction for this reason. So if we know energy can't be created or destroyed, we can figure out in a chemical reaction how much energy was released or absorbed just by looking at the thermochemistry. What this also means is if you think that you have created a perpetual motion machine, you're wrong. I'm sorry, I don't want to there have been times in my life where I've learned about new scientific concepts. And I'm like, oh my God, you totally can use that to make a perpetual motion machine. We'll get energy for free and the world will be happy and blah, 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 blah. No, sorry. Unless you do science a way that no other scientist has ever done. And some of you may do science that many of you may do science that no other scientist has ever done. But physics and chemistry as we know it does not allow for a perpetual motion machine. But if you do come up with one, let me know, and I'll help you patent it for a cut of the money. Okay, so we know that the energy of the universe is constant, so we can quantify energy change in a chemical reaction. So we're going to talk about this term enthalpy. So enthalpy is technically the thermal energy. I've never actually taken a sip of water on the mic, and if you're at home watching this and it was really loud, I'm sorry. That's a little weird. So the thermal energy content of a system at constant pressure is the enthalpy. For our purposes, we're going to talk about enthalpy really as chemical potential energy. And it comes from the interactions, attractions, and repulsions amongst atoms and molecules. So think about it as potential energy change. We really don't higher level thermodynamics courses in college. As a chemical engineer, I had to take 2 semesters of thermodynamics, which is all this stuff. and this is thermochemistry and thermodynamics. You'll talk a lot about enthalpy. We're really mostly concerned with change in enthalpy, right? So we're not going to be looking at absolutes. We're going to be looking at deltas. So the question was, does ATP have more enthalpy than ADP? So I don't know biology well enough to know that, but I would imagine when you react ATP and get ADP, that's an exothermic reaction. So then it would have more enthalpy than ADP. Because, as we'll see on this next slide, change in enthalpy is delta H. If delta H is positive, then the potential energy of the substances is, what do you think? Is it going up or going down? If delta H is positive, yep, the potential energy of the substance is increasing. And the reaction is what? Is it endo or exo? Endo, you're putting it into. Delta H is negative, then the potential energy of the substances is decreasing. And the reaction is exothermic. Now, which one of these do you think is more favorable in the universe? Putting energy in or getting energy out? Talk about it at your table. Which one of these is more favorable in theory, endothermic or exothermic? All right, so what do you guys think? Let me get a volunteer. Endo, exo. Why do you think? Yeah, things are going to want to go to lower potential energy. We talked about that, I think, earlier in the year, where systems, reactions tend to want to go to lower potential energy. They're more stable and they have lower potential energy. So they're going to want to get rid of whatever potential energy they have. So reactions tend to be more favorable if they're exothermic. Okay. Understanding intermolecular forces. Qualitative understanding. So we're not putting numbers yet. If I have two water molecules, this is something that I'm hoping you guys would have realized even from problem set 1. If I want to separate them, what happens to the potential energy if I separate attractive objects? Yeah. So my delta H is greater than 0 because I have to put energy in to move them apart. So I know for this, my delta H is greater than 0. If I allow them to come together, delta H is less than 0, and energy comes out. Now, this is true for ions as well. This is true for atoms in a covalent bond. True for ions, atoms in a bond, molecules, etc. So it doesn't just have to be a bond. One of the problems that came up a lot as I was grading test 2 and the cumulative is you guys talking about intermolecular forces as a bond. That's not a bond that's breaking. You're just disrupting the intermolecular forces, right? But if we separate things like ions that want to be together, or atoms in a covalent bond, or molecules that are attracted to one another, we have to put energy in. And if we let them come together, energy comes out. Okay. So, you know, sometimes I like jump ahead of myself. I like don't think of what slides are coming next, and I sort of give you the answers already. So let's just go through it just for fun. Breaking bonds. Is this, what would happen to delta H if you're breaking bonds? Increase. You can also think of it as energy in or endothermic. Because if they're in a bond, they're obviously attracted to one another. And breaking bonds, delta H is less than 0. Energy comes out, and it's exothermic. So we're not doing anything new other than putting this new term of delta H to what we were talking about. All right. So let's get a qualitative understanding of how this works. If I have, let's see, how do I want to do this? So I have, we'll just do a very simple one. This one came up on the cumulative as well, the idea of H2. So if I have 2 H atoms, are they attractive, repulsive, or indifferent? Would these want to come together to form a bond? Yes, no? Wow, that I had a yes and a no as the answer. That would be indifferent. They form H2, so what's going to happen? They're attracted to one another, so they're going to come together. So they'll come together. They'll make this. So what's happening here? I have attracted objects coming closer together. What's happening to the energy of this system? Yeah, delta H is less than 0. I'll also give it like, is that like a winky? I don't know. Like a little wink. They're like happy. They're like bonding together. They're coming together. Creepy wink. They're like, they want to be together. They come together. Their potential energy decreases. Energy goes out. And then something happens in their lives that tears them apart. I don't know. What's something that could happen? One of them has to, yeah, divorce. I was thinking one of them has to move to another town. One of them has to move to New York for a job. Very specific. I like it. What's that? One bonded to oxygen. That cheater. They need to find themselves. They need to explore and see what other molecules they can make. Okay, we took this way too far. All right. Here, it took that energy in to split them apart, and then you don't think I should draw the faces? Oh, I just got really, really burned. See, so you know what? Just because of that, I'm going to spend extra time on this face. Give it some tears. This is my heart breaking because Azika made fun of my drawings. Look, I'll even make it me. I'm going to edit this out. They should be in the Google Drive. Okay. All right, we're going to take a little pause here. Take a minute. Talk to yourself about how wonderful my drawing is. That's me. I'm crying because Azika made fun of me. I saved it in the wrong place. I put it under answers now. It should be there. All right. So we are back. I do think that's quite the self-portrait, though. Okay. So, again, guys, this is nothing like this last 30 minutes, other than being a little silly at times, is nothing that's particularly new to you guys. We're just sort of reviewing where we came from. So now, we're going to start talking about things you should know. So, physical changes, such as phase changes and dissolving, involve breaking up certain intermolecular interactions and allowing others to occur. Reactions generally, this is chemical reactions, not phase changes, generally involve bond breaking and bond, this should be and or bond making. And when a reaction happens, energy will either be absorbed or released. Here's like a huge idea. It depends on the relative strength of the attractions that are broken and the relative strength of attractions that are being made. So this came up, I think it was on the second test. So we've already talked about this, right? The question about the ions and releasing energy. Like when you put calcium chloride or calcium fluoride in water, it releases energy. Why does it release energy? Because the water and the ions are more attracted to each other than they were to their original partners. Okay. So, bond energy. Give me a color. I heard green. All right. So, all bonds have a numerical energy value associated with them. And generally you'll find this number in terms of kilojoules per mole. So you can actually look up the bond energy values. And I think on problem set 11 you're going to have to do that, in fact. So this is the energy required to break what do I want to say? To break the bond and the energy released when the bond is made. So you're going to find this bond energy value. It's going to be a positive number. That's the energy that is required to break, in this case, 1 mole of those bonds. If those bonds were made, that value would be negative, but the same magnitude. Okay. So say to break, do I have these numbers? To break a ClCl bond, to break 1 mole of ClCl bonds, it takes 242 kilojoules. And if you're going to make a ClCl bond, that's how much energy you'd get out. And these values are provided or found in a table. Now, the interesting thing is, when you do problem set 11, we based all of our bond energy values off the values in the book. These are empirically determined, right? So scientists have said, okay, we're doing a bunch of experiments, we're doing some combustion, we're doing chemical changes. This is what the bond energy values are. But these are just really averages. So the bond energy values you find in the book are not perfect. They might actually be different than ones you find on the internet. So your values that you get if you get your bond energy values from the internet will be different from the ones in the book. And they're just averages because it matters what else is in that molecule, right? So if you say, like, not all CC bonds are equal. So in the real world, I'm going to put real world, not all carbon-carbon single bonds are equal, right? Depends on what else is bonded on the other sides. If you have like electronegative things here, on one side and not on the other. That might change your bond energy value. But we, in this class, are going to treat all carbon-carbon single bonds as equal. And whatever it says in the book or the table is what you're going to use for how much energy it takes to break this or make it. Does that make sense? Okay, so let's do an example. Bless you. So use bond energy values from the book to estimate the delta H for this reaction. Well, you don't have your books in front of you. I mean, I have a bunch, but we'll not do that. Here's your first step. Draw your Lewis dot symbols. So I want you guys to take a minute, draw Lewis symbols for each of your reactants and your single product. Okay, so this is what you should have gotten. Now, it doesn't matter where you put the CLs. You could have put them on the same carbon. You could have put them on different carbons. You could have put them anywhere around the carbons. I wasn't being specific at this point. Okay, so this is what you should have gotten. Now what we need to do is figure out what bonds got broken and what bonds got made. So you're going to have the advantage of looking at this right in front of you. I'm going to move to the next slide. So I'm just going to rewrite. Whoops, that's 4 plus Cl2 makes C2H4Cl2. So at your tables, figure out what bonds were broken and what bonds were made in this chemical reaction. So talk about it with each other. All right, I'm going to go to the cards. Ooh, I haven't used the cards in like a very long time, I feel like. All right. Ben, your card came up. Sorry. What bonds got broken here? All right, 2 Cl atoms. That's pretty good recovery. So that bond got broken. What else got broken? Caitlin, what else got broken? So this was 1, and then 2. You can do it one of 2 ways. You can say it was the CC pi bond, or you can say both bonds got broken. You can do it either way. I'm actually going to do it this way because it's a little bit easier. So, and then what bonds got made, Thomas? Two CCLs, right? Now, if I do it this way, if I say I broke the C double bond, if I say I broke both of them, what would I have to put over here? So let's pretend that I say I split the carbons totally apart. So what would I have to make over here? Let's look back here. If I broke these totally, so let's pretend I split them apart totally, what do I have to make? Just a single bond, right? So that's 1, and that's 2. Okay, so I'm going to do it this way. Now, I'm going to pretend you all looked in your books And you got values for this. And so to break this is 614 kilojoules per mole. This is 242 kilojoules per mole. This is 328 kilojoules per mole. And this is 348 kilojoules per mole. So figure out at your tables, what is the total amount of energy absorbed or released by this reaction? All right. So, Alex, what did you get for the amount of energy required to break the bonds? Now, is that energy in or energy out? So that's positive, right? All right. So, Joanna, what did you get for the energy from the bonds being made? Okay. I don't agree. Okay, so here's the trick. You have 2 CCl bonds made for every one, so you have to multiply this by 2. Because you have to break it twice. So 656 plus 348. Who can get it? Who does mental math quick? I got it. What's that? Very close. You would have gotten full credit on a test. Yeah, 1,004. Now, this is energy that comes from the bonds being made. So Carter, what sign do I put with this? Negative, so that's energy out. And then I add them up, right? I add the positive and the negative. So I should get 144, negative 148. Negative 140, that is not English. Negative 148 kilojoules per mole. So in this chemical reaction, if I do 1 mole of this chemical reaction, that means I would release 148 kilojoules of energy. The next 2 slides are not actually on your sheet. So you need to be able to do this. You need to be able to look at bonds broken, bonds made, put an energy value to them, and figure out the total energy involved in the reaction. That's one thing you need to be able to do. The other thing you need to be able to do is one that's not explicitly written here, but I think shows up in your problem set. So can I move on? Are we okay? How much energy is released in joules when 10 grams of methane is combusted? Find a place to write it down, like in a margin or something. I want you guys to think about this one for a minute. We have 18 more minutes in class, and these are the last 2 slides we're going to do. So think about it. How would you figure out how much energy in joules is released when 10 grams of methane is combusted? So talk about it at your table. So you're going to need some information that you don't have. So, Griffin, what do you guys need in order to do this? You need the bond energy values. So that is something that you need to do. So you need to come up with a combustion reaction, which you all know how to do after watching lecture 10. Right. All right. So combustion means you're reacting with oxygen. If you have a hydrocarbon, you're just making carbon dioxide and water. So then let's do our Lewis structures. All right. So once you have your Lewis structures, you move on. And what's the next step you're going to need to do? Carter. Find which bonds are broken, which are formed. So I'm going to move. Is it all right if I move on to the next slide? Yeah. So if you already have this copied down, move on to the next slide and figure out what bonds are broken, what bonds are made. And I'm going to put some values up on the board to help you out. All right. Okay. So at your tables, I'm just going to write stuff up on the board. I want you guys to talk about it, and then you can look up to see if I'm writing the right values for you. I trust you guys enough. Okay, don't worry about the 10 gram part yet. We're going to come up. All right. So you guys should be able to figure out the bonds broken, bonds made. So blank for G block, blank for G block. Sophia, amount of energy that went in to break the bonds. 2,612 kilojoules per mole. And then Daniel, energy out. Haven't finished it yet? 2,632. Okay. About the same. I trust you. I would not count either of those as really different values. All right. Made. Do you have the made? 34, 34. Wait, 34, 34. Kilojoules per mole. Let me make that better. Do people agree? Okay. So then what is the total delta H for this reaction? Negative 802. All right, so where do we go from there to figure out how much energy is released when 10 grams of methane is combusted? You have to find the moles of methane. So we have 10 grams of methane. The molar mass of methane is 16. So we have 0.625 moles of methane. So what do you think we do with this number and this number? Multiply. So, Griffin, shout out a color. I can only do one. Yeah. I need a non-onyx color. Lilac. I'll do lilac. All right. So I have negative 802 kilojoules per mole times, guys, times 0.625 moles. The moles cross out, and I get about right over 500, right? It should be negative 500.1 or 2 or something. Negative 500 point. Oh, crap. Yeah. It's easy because this is 5/8 and this is 100. So, okay. So this is the answer. Now, I'm going to beseech you, watch your units and your coefficients. So, if in my chemical reaction if I said instead of 10 grams of methane, I said 10 grams of oxygen, you'd have to figure out your moles of oxygen and then divide that by 2. Because for every mole of reaction that happens here, you use 2 moles of oxygen, right? So that's going to be your trick. Your trick is to look at the coefficients in the chemical equation and make sure you're using it. They very well could be. Yep, it's just kilojoules. So if it says joules, leave it in joules. So this is negative 501,250 joules. Yeah. Make sure you answer the question the right way and don't do what Mr. Bennett just did and leave your answer because you were so excited that you got it. Make sure you have the right unit. I even said watch your units, and I didn't watch my units. So do as I say, not as I do, I guess is the takeaway. Okay, so today we did a lot. I mean, you still have 7 minutes of class that you can start looking at problem set 10. But that is all. This is all you need to know for the first half of thermochemistry. I'll finish the second half of thermochemistry today, and chapter 11 will be done.